Welcome to the Deep Dive. This is where we dig into the sources you send our way, pull out the really interesting stuff, and basically give you the inside scoop.
Exactly. Making you seriously well-informed, fast.
And today we're diving deep into the world of magnets. Pretty fascinating material you sent.
Oh yeah, we're going way beyond just fridge magnets here. This is about the fundamental power, how it was discovered, and even how our whole planet acts like one giant magnet.
Okay, let's start at the start then. The info we have points way back, like 800 BC, to a place called Magnesia.
That's the story, yeah. People there found this particular iron ore, magnetite, they eventually called it, that had this weird ability to pull iron towards it.
Just finding a rock that does that, it's
Right.
kind of amazing. Was it just a curiosity back then, or did they, use it for anything?
Well, what's really interesting is they noticed something else pretty quickly. If you hung a piece of this magnetite, let it swing freely,
Yeah.
it didn't just spin randomly, it would consistently line itself up, pointing north-south,
Ah,
which is why they started calling it lodestone, literally a leading stone.
a leading stone. Okay. You can immediately see how useful that would be for finding your way, even way back then.
Definitely hinted at something more, some kind of directional property.
And this magnetite stuff, chemically, what actually is it?
So the material clarifies it's a specific iron oxide. Feoa is the formula, a particular mix of iron and oxygen.
Gotcha.
And that ability, that pull on iron, that's what we define as magnetism. And the force doing the pulling, that's the magnetic force. Simple as that.
Right, but it's not like everything is magnetic, is it? The sources make a distinction.
Absolutely. You've got your magnetic substances, the ones that magnets actually attract. Think iron, cobalt, nickel. Those are the main ones mentioned.
The magnetic club, basically.
Sort of, yeah. And then there's everything else.
The non-magnetic stuff, like...
Well, things like aluminum, copper, wood,
Yeah.
plastic. You put a magnet near them, and, well, nothing happens. They just aren't affected by that magnetic pull.
Okay, so magnetic, non-magnetic. Got it. Now let's dig into what makes a magnet tick. Its properties. The first one mentioned is the attractive property.
Yes, the classic one. The thing everyone knows, magnets attract magnetic stuff. And a really good way to see this is with iron filings.
Oh yeah, the experiment where you sprinkle them around a bar magnet.
Exactly. You see this really clear pattern form.
And the sources have a figure for this, 12.1. You can really see the filings bunching up right at the ends of the magnet, but almost nothing in the middle.
Precisely. It's like all the strength is focused there.
So the power is concentrated at the tips.
Which leads us straight to the idea of magnetic poles, these areas where the pole is strongest. And they're actually slightly inside the very ends. Usually you have two, a north pole and a south pole.
And this isn't just for bar magnets, right? What about those U-shaped ones, horseshoe magnets?
Same deal. They have poles too, right at their open ends. Figure 12.2 shows a dip one in iron filings, and you'll see the filings cling right to those ends.
Okay, so attraction and poles. Makes sense. But then there's this other thing, the directive property. What's that about?
Well, that takes us back to the lodestone. Remember how it pointed north-south?
Yeah.
If you do the same with any bar magnet today, suspend it so it can turn freely, like horizontally it'll do the same thing. It settles down, pointing roughly north-south. Figure 12.3 shows this.
So one end just naturally wants to point towards the geographic north and the other towards the south. That seems fundamental.
It really is.
Yeah.
And we define the poles based on this. The end pointing north, that's the magnet's north pole. The end pointing south, that's the south pole.
And that whole tendency, the north-south alignment, that's the directive property.
Exactly. And why we label the poles N and S, activity 1 in the sources, really drives home that most of the magnet's oomph is right there at the poles.
Right. Now, what if you bring two magnets near each other? It's not always attraction, is it?
Definitely not. This is where pole interaction comes in. Figure 12.4 shows this really well. Bring two north poles close, they push apart, repel. Same thing if you bring two south poles together. They repel too.
But north to south.
Now that's attraction. They pull together.
So the rule is, like poles repel, unlike poles attract.
That's the fundamental rule.
Yeah.
You got it.
Okay. What if, say, I try to break a magnet in half, can I get just a north pole on its own?
Good question. But nope, doesn't work like that.
No.
Figure 12.5 illustrates this. You break a magnet and bam! Each piece instantly becomes a brand new, smaller magnet with its own north and south pole.
Seriously, so you can keep breaking it smaller and smaller.
And every single piece will still have both a north and a south pole. It seems you just can't isolate a single pole. They always come in pairs.
Wow, so magnetism is always like a two-pole thing, dipolar.
That seems to be the case, yeah. Poles always exist in pairs.
Fascinating. Okay, this seems like a perfect lead-in to the magnetic compass. That sounds like it uses this directive property directly.
Absolutely. It's a brilliant application. The description we have says it's basically a small magnetic needle balanced on a pivot so it can spin freely, usually inside a little brass box with a glass top.
And one end is usually painted red.
Right. That's the north-seeking end. Makes it easy to read. Figure 12.6 shows a typical compass.
So how does this little gadget actually work for navigation?
Well, because that needle is a magnet, it uses its directive property. It lines itself up with the Earth's own magnetic field, pointing north-south. So the red end points towards magnetic north.
Which is pretty close to geographic north, right?
Very close, yeah.
Yeah.
Close enough to be incredibly useful for finding your way. Think of travelers, sailors, explorers. For centuries, this was vital. Activity 2 even shows how you could make a simple one yourself.
Cool. Okay, so magnets attract, they have poles, they interact, they point north-south, and we use that in compasses. But there's something bigger going on, isn't there? This idea of a magnetic field.
That's right. It's not just about the magnet itself.
Uh-huh.
Think back to the iron filings again, figure 12.7. That pattern they form.
Yeah, those curved lines.
That pattern shows us something invisible. It reveals the magnet's area of influence.
Like a force field.
Exactly. The space around the magnet where you can actually detect its magnetic force, that's what we call the magnetic field.
Okay, an invisible field. How do we, map it out or visualize it better than just with filings?
Well, one way is using a compass again,
Ah.
like in figures 12.8 and 12.9. Normally, a compass points north-south, right?
Right.
But bring it near a strong bar magnet, and its needle swings away from north-south. It lines up with the magnet's field instead.
Ah, I see.
And if you move the compass around the magnet, placing it at different spots, the needle will point in different directions, tracing out these sort of invisible pathways.
These are the magnetic lines of force.
Precisely. The compass needle basically aligns itself along the direction of the magnetic line of force at whatever point you place it.
And the sources show different patterns for these lines in figure 12.10, like around a single bar magnet or between two magnets.
Yeah, look at the single bar magnet. The lines seem to come out of the North Pole, loop around, and go into the South Pole.
And when you put unlike poles together, north facing south.
The lines kind of bridge the gap between them. Shows the attraction.
But if you put poles facing each other, say two norths.
Then the lines look like they're bending away, pushing each other apart, visualizing the repulsion.
And for the horseshoe magnet?
The lines are really concentrated right between the poles in that gap. Shows where the field is strongest there.
These lines seem pretty important. Do they have rules, like characteristics?
They do. Key properties mentioned are, 1, each line is a continuous closed loop. They go through the magnet too, actually.
Okay.
2, outside the magnet, they always go from the North Pole to the South Pole. 3, and this is crucial, they never cross each other.
Why not?
Because at any single point in space, the magnetic force can only point in one direction. So the lines representing that direction can't intersect.
Makes sense. What else?
Well, 4, they are packed closer together where the field is strong, like near the poles, and spread out where it's weaker. And 5, as we saw, they dictate which way a compass needle points.
Right. Now, prepare for the really big one. The Earth itself is a giant magnet.
That's the mind-blowing part, isn't it? The sources state it quite clearly. The thinking is there's effectively a huge bar magnet deep inside the Earth.
But it's not lined up perfectly with the north and south poles we use on maps, is it?
No, it's tilted. The magnetic axis is off by about 19 degrees from the geographic axis. Figure 12.11 shows this tilt.
And it apparently plays a role in protecting us from space radiation, too, the magnetosphere.
Exactly. That magnetic field extends way out into space and shields us from a lot of nasty charged particles coming from the sun, the solar wind. It's pretty vital.
Okay, but here's the bit that always twists my brain a little. The magnetic pole up near the geographic North Pole. That's actually a magnetic South Pole.
That's the convention, yes. It's confusing, but think about it. The North Pole of your compass needle, the north-seeking pole, must be attracted to the opposite pole type.
So it's attracted to the Earth's magnetic South Pole, which just happens to be located near the geographic North Pole.
Precisely. And the Earth's magnetic North Pole is down near the geographic South Pole.
Wow. Okay. And this whole planetary field is just called the Earth's magnetic field.
Yep, that's the term.
And how do we even know this is real? What's the evidence?
Well, 2 main things mentioned. First, the compass itself. The fact that a freely suspended magnet always points north-south is direct evidence it's interacting with a larger field, the Earth's field.
Okay, that makes sense. And the second?
If you take a piece of soft iron, just a plain iron rod, and buried in the ground, pointing north-south for a long time,
Yeah.
it actually becomes magnetized. The Earth's field induces magnetism in it over time.
Whoa. And figure 12.12 just reminds us again, the magnetic poles and geographic poles aren't in the exact same spots.
Correct. They are offset.
Okay, wow. Let's try and wrap our heads around this with a quick recap. So, magnets pull on iron. They point north-south if free. Things attracted are magnetic.
Right. The north pole of the magnet points to Earth's geographic north.
Like poles push away, unlike poles pull together.
Yep, repel and attract. And you can't get a pole by itself always in pairs.
The magnetic field is that invisible zone of force around the magnet, strongest at the poles, weakest, basically zero in the middle.
Correct. And that north-south pointing thing, the directive property, is why compasses work.
That compass needle shows us the north-south line. But near another magnet, it'll point differently, tracing those magnetic field lines.
Which are these continuous curves going from North Pole to South Pole outside the magnet.
And the big finale, the Earth itself is basically a giant magnet.
That sums up the core ideas from the material really well, from,
Yeah.
That ancient discovery in magnesia to these complex field lines and the Earth's own magnetism. It's quite a journey.
It really is, and it leaves you thinking. The sources mentioned the Earth's magnetic poles aren't perfectly fixed. They're offset, and they actually wander over time.
Yeah, magnetic drift.
So what does that mean long-term for navigation, which relied on that fixed-ish point for so long? And what about animals? So many birds and turtles and things navigate using the magnetic field for migrations.
That's a really provocative thought. How do gradual, or maybe even sometimes rapid, shifts in the Earth's magnetic poles affect those incredible journeys over geologic time or even human timescales?
Yeah, definitely something to chew on. Makes you want to look more into how dynamic that planetary field really is.